Okay, so we got a galvanic cell here. And they're pretty basic how they work. You have a cathode and you have an anode, and they're in solution. They're connected by a salt bridge, so it allows ions to flow from one to the other. This is a voltmeter, it's just to measure the volts running through the wire. So copper in this case is the cathode because it wants to gain electrons. So therefore we'll label this plus. Zinc loses electrons, therefore it's the anode because the zinc is being oxidized. So since zinc is losing the electrons and copper wants to gain them, the electrons flow this way through the wire. And when it comes to the salt bridge, the anions, the positive ones, flow towards the cathode, and the negative anions flow towards the anode. And honestly, that's about it. That's what we got to work with here. Since zinc is the anode, it's being oxidized, which means it's losing electrons, which are going to flow this way to copper at the cathode, which wants to gain electrons because it's being reduced. But since zinc is losing electrons, that creates zinc 2+. So therefore, the negative ions want to flow towards the positive zinc cathode or anode. And also, copper ends up with a Cu2- charge. So therefore, the positive ions want to flow towards the cathode. Here's the math for this equation. So it's E0 equals the E of the cathode minus the E of the anode. In this case, copper is our cathode. So we go to our book right here and find copper right there and see that it's 0.337, which goes here. Next is the anode, which is zinc, which we see right here with a negative 0.763. So we get 0.337 minus a negative 0.763, which equals 1.1 volts. So the expected voltage of this problem is 1.1 volts, assuming that both molarities of each solution is 1.0. So we're going to introduce a new kind of little section to this chapter. It's called cell notation, and it's pretty simple. So you start with the anode, which was zinc, and then you draw one line to represent the difference as it goes into solution, which would be, in our imaginary experiment, zinc sulfate. And the double line represents the salt bridge where the ions cross. And then after that, you do the anode solution or cathode solution of copper sulfate, and then the cathode itself, which is copper. Next are some real-world applications for a galvanic cell. Portable power comes from galvanic cells, so like obviously my favorite is the Tesla Roadster. So like, you know, got a nice car right here, just got some wheels on it and stuff, and you know, we've got the battery probably somewhere right here. And then, you know, it goes super fast. And then another one we have. So in our demonstration, we use the wet cell, but there is such thing as a dry cell. It's called a Leclanche dry cell. It's typically used in flashlights, like this one here. Also, they use them in button batteries and nickel cadmium rechargeable batteries. My favorite use for these are in pacemakers for your heart. And keeps people alive, so you know, pretty powerful stuff. Pause it. The biggest concern with galvanic cell batteries is disposing of them, because usually the materials in them use heavy metals, which are extremely toxic and could burn the environment. And also the other downside is they're not very efficient. They only collect about 30% of the potential energy in the cell.